Let's begin. Welcome back from spring break. I know you've remembered everything about statistics and you're coming in fresh. I'll do a quick reminder to pick up where we left off because we left off at a climactic point. Was very, very important. But before we get into that, exam 2 on the syllabus, it says March 27th. Unfortunately, we cannot make that because I need to at least have this week's homework submitted next Thursday, which is the 27th, so it's unfair to do that on you. So we're going to move it to April 1st. The exam 2 is going to be on April 1st. It's not going to cover a lot, so central limit theorem and confidence intervals. Obviously, the continuous distributions, we're still working with continuous distributions, so you just need to still understand those. But definitely central limit theorem and confidence intervals. And like I said in the announcement, there's no previous exams I can share with you because this is the first time I'm teaching this. So, you're welcome. So I'll use your exams as previous exams next year. Okay, so that's the sacrifice you're making. But I'll do the Q&A thing like we did in the exam 1. So you'll submit your questions. I'll compile them, whether we have a session about those or not. That remains to be determined. We're a little kind of late, running behind on things. So we have a lot to cover today. I want to finish with confidence intervals. Maybe some will spill over because we are going to have a big activity with the radon data. So if some of it spills over for Thursday, that's okay. So where we left off last time, we started on, so remember we did confidence intervals for a single sample. We looked both at the mean and the standard deviation or variance. We looked at cases where we know the standard deviation of the population, which is a critical quantity to recognize. If we didn't know that, we had to estimate it from the sample, but the uncertainty coming from the sample standard deviation led us to deduce that we have to use a t-distribution to accommodate for that uncertainty. For variances and standard deviation, we use the chi-squared distribution. So that's for a single sample. Now we want to look at two populations, and eventually we might need to look at many populations, right? Not just two. Okay. But the case for two is, we call that two treatments. You might have 3 or 4 treatments, for example. So it's doable in the same procedure. And when comparing two populations, you might ask, why do we need to compare two populations? Always think of it as a treatment. If I install a radon mitigation system in my basement, is it going to mitigate the radon? So data before radon system was installed, data after the radon system was installed. In your homework, you're going to analyze the temperature in my garage, okay, before and after I installed a mini split in the garage to tell me if there was a noticeable cooling effect or whether it's not statistically significant. So I can call the guy and have him refund me my money or just come and repair things, right? So, real data, real stuff, statistical comparisons will be useful. So that's where we need to compare two populations. And typically, you're looking at means. Why do we always look at means? And because we can use the central limit theorem. The central limit theorem is critical in telling us all sampling distributions of means are normally distributed or t-distributed, etc. It allows us to use those tools to generalize, okay? So that's the setting. With two populations, I'm going to remind you quickly how we derive the confidence interval for two populations last time. But I did that last time, probably forgot it, so we'll run through it quickly. I have two populations. Population 1, I'm going to call its mean, its true mean, and its true standard deviation, mu1 and sigma 1. Sample 1, I'm going to refer that to x. That's the sample from population 1. And the sample 1 has size n1, similar for population 2, mu2, sigma 2. But we're going to call the sample y, and it's of size n2. Now, the single point, the confidence interval for this sample alone, we learned that this is x bar, so that's an estimator for the true mean. It's plus or minus, so the true mean for population 1 is between x bar minus z alpha over 2, etc., sigma 1 or square root of n1, and x bar plus. X bar is the sample mean, so you take a sample, you compute its mean, plus or minus this value. That gives you a range within a certain confidence where the true population mean is. Remember, we don't know the true population mean. We only know the sample mean. Okay, in this case, we're starting off knowing the standard deviation for the population. That's not going to be the case in practice, but we're going to start here because it allows us to do the math correctly. Same thing, these are the confidence intervals for just population 1 or population 2. And so you might ask, why can't we just take the difference? If I want to compare these two populations, I'm looking at the difference at an estimate for where mu1 minus mu2 is going to be. Okay, so that's when I'm comparing two populations. I want to estimate where the difference in their means, in their true means, is going to be. So you might say, why not take the difference between x bar and y bar, right? Because that's a confidence interval for population 1, confidence interval for population 2, and because everything in the world is linear and superposition, quantum mechanics, right? Superposition stuff. So let's just take the difference between the two. And if you do that, x bar minus y bar, you get plus or minus z alpha over 2. So the mean, in other words, the difference in means is between these two values, okay? X bar minus y bar plus or minus this quantity, okay? And last time I said this is wrong. It is very wrong. It's not correct because we have to think about this differently. And the reality is as follows. So if we look at a single confidence interval, I want to rewrite this formula as follows. So I'm going to take the square root of sigma squared over n. What misled us here is the fact that we have a sigma over here. The true way of writing this should be in terms of expected values. In other words, here I should have the variance of x bar rather than sigma squared over n, okay? So when I have the variance of x bar in this formula, then this confidence interval is interpreted as follows. X bar is my random variable, and var of x bar is the variance of that random variable. Then the correct way to look at the difference between two populations is to take the difference between the two samples, x bar minus y bar, and say that that in and of itself is a random variable. Because x bar is a random variable, y bar is a random variable, therefore x bar minus y bar is also a random variable. And now if you follow that same strategy by that same logic, then the confidence interval for x bar minus y bar should be z alpha over 2 square root of the variance of x bar minus y bar. Okay? That is the true formula. And then when you do that, you get the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, only if x bar and y bar are, if x and y are independent. And it's not this guy. So, excuse me. It's like the difference between the sum of the squares or the squares of the sum. Okay? So here you're taking the square root of the variance, not the variance of square roots, something like that. Okay? So this is not the correct formula. You can't take the single confidence intervals and subtract them. You are missing a lot when you do that. You're committing a grave error. Let's put it this way. So you have to treat x bar minus y bar as its own random variable and just follow that logic, and you'll get the confidence interval just doing that. Now in the textbook, what you'll see people just saying, hey, this is the formula for difference between two populations. You'll ask why. There's no why. Now obviously there's deeper proofs. Okay, I like to be somewhere in the middle, give a slight intuitive understanding for why we have to construct the confidence interval this way. So there is power in looking at variance and these formulas, right? Expected value and variance versus just looking at the standard deviation. Okay, so now you know that these are our confidence intervals for two populations or two samples with a known standard deviation. Okay, I'm going to start with a simple example. So we know how to do all of this. We know how to compute z alpha over 2, and you know how to do a square root, hopefully, and take a fraction, etc. So we know how to compute all of this. All right, so let's start with a simple example. A researcher is looking at the study habits of college students. A random sample of 42 freshmen reported a mean study time of 15 hours per week. And a random sample of 39 seniors reported a mean study time of 23 hours per week. Okay, so now the question is, are they really studying more? Is this enough evidence that the seniors are actually studying more than the freshmen? The question is to construct a 95% confidence interval to estimate the true difference between the average time per week that freshmen and seniors spend studying. Assume that study times for freshmen have a population standard deviation of 4.7 hours per week, and for seniors, the standard deviation is 5.2 hours per week. So we have everything we need to construct now the difference in means for the population of freshmen and seniors. Here we only have samples. We only have the means of the samples. For freshmen, it's 15 hours per week, and for seniors, it's 23 hours per week. You could say, oh, 23 is larger than 15, so they might be studying more. Well, I don't know, because that's only a sample, right? This sample is studying more than the other sample, but is this true for the population? Okay, so that's the question. Are all seniors studying much more than all freshmen? Right, that's the question. All right, so first thing is you want to choose your population, your populations, and it doesn't matter which population you assign as population 1, which population you assign as population 2. The difference will be you might either get a negative confidence interval or a positive confidence interval, right? If you put mu1 minus mu2 or mu2 minus mu1, whichever value is larger. So we're going to assign population 1 as the freshman, and we're going to call that X with a sigma of 4.7 hours per week. Population 2 is the seniors. We're going to call that Y with a sigma of 5.2 hours per week. Now my point estimator, remember the point estimate is just the single value no interval, is obviously the difference between the sample means, which is X bar minus Y bar, population 1 minus population 2 means. So that's 15 minus 23, that's minus 8 hours per week. What does this mean? It means that freshmen are studying 8 hours less than seniors. That's the negative value, because we put freshmen as our population 1. If you had swapped those, then you're going to get the number 8, and then you would say that seniors are studying 8 hours more than freshmen. Okay? Now, populations are independent, and therefore we can use what we deduced before. In the vast majority of cases, populations will be independent here. When they are dependent, it gets very complicated. And with a confidence interval, so I have sigma 1 and 1, I have sigma 2 and 2. I need z alpha over 2. I need to get alpha from the confidence level, which is 95%. So alpha is 0.05, and alpha over 2 is 0.025. So you get z alpha over 2 as 1.96. And you plug in the number, and you get the error, or the standard error, 2.164257. What are the units here? Hours per week. Okay? And then you plug that back in, so you get x bar minus y bar minus e, and x bar minus y bar plus e. So you get that the difference between these two population means, or the mean time spent per week on studying, is between minus 10.2 hours per week and minus 5.8 hours per week. So what does this mean? It means that because the number is negative and freshmen is 1 and seniors is 2, it means that freshmen are studying anywhere between minus 10, studying less than seniors anywhere from 5.8 hours to 10.2 hours less. Okay, that's what the negative numbers mean. If you had swapped the meaning of the populations, if 1 was seniors and 2 was freshmen, you're going to get 5.8 to 10.2, and then you'll say seniors are studying more than freshmen by 5.8 to 10.2 hours, okay, per week. One more thing. This is my confidence interval up to 95%. What do I mean by that? It means that if I were to sample populations from these samples from these two populations, I am confident that 95% of those samples, the mean value is going to be the mean difference. The difference between means is going to be here, between here and here. Okay? There's a 5% chance that your true means is going to be outside this interval. Okay? So now you might say, like, why don't we go to 99% interval or 99.999 like the bacteria thing, right? Because it starts committing certain types of error that we will learn in hypothesis testing. Okay? All right. Do you have a question?
Yeah, I was curious how we got the A over 2.
Yeah, we've done this before. So yeah, we can't. So from here onwards, you know how to calculate Z alpha over 2, T alpha over 2. There's going to be the chi-squared alpha or 1 minus alpha. You need to know these things, okay? So we can't go back to that, all right? We need to start building these formulas. All right. Okay, another example. An automotive repair shop advertises that using a fuel additive will decrease the wear and tear on an engine. It's like that Jiffy Lube, the flailing guy with the, well, come, put an additive here. We're going to fix your oil and whatever. Good guys at Jiffy Lube, good guys. Okay, so an independent researcher collected, like, don't go up to Jiffy Lube and tell the guy, what is your evidence that this additive, what is your confidence interval? You're going to be like, okay, no. So, don't do that. It's weird. An independent researcher collected data from 50 randomly selected cars that used the fuel additive and found that the mean cost of engine repairs was $3,250. He then collected data from 55 randomly selected cars that did not use the fuel additive and found that the mean cost of engine repairs was a little higher, $3,445. Okay? So it's a little higher, but not too high. But is that enough evidence that the fuel additive actually reduces repair costs? I mean, this is an interesting case, right? Because the numbers are close, yet they're smaller, so but $200 less, right? So that might be worth it. The population standard deviation for engine repair costs for cars that do not use the fuel additive is $812, and the standard deviation for cars that do use the additive is $748. Okay, it's just a lot of word stuff here. Construct an 85% confidence interval to estimate the true difference between the mean costs of engine repairs for cars that use the fuel additive and those that do not. So here again we took a sample from cars that use the additive, a sample that didn't use the additive, so that's a treatment. Using the additive is a treatment, and we're asking a question. If it's true for these samples that the mean cost of doing the additive is less than the mean cost of no additive, is this true for all cars? Is this true for the population, right? The population of cars that did not use it versus the population of cars that used it. It's a really useful tool, man. Okay, so population 1 is cars with additive. So we call that X. We got 50 cars, and sigma 1 is 748. Population 2 is cars without additive. We call that Y, 55 cars in our sample, and 812 for the sigma 2. And then the point estimator is the difference between the sample means. And our population 1 was the with additive, so 3250 minus 3445, and that gives me minus 195. So this means that in my sample, the cars with additive paid $195 less in repair costs, okay? Or the cars without additive spent $195 more on repair costs, okay? Samples are independent, and therefore we can use this estimator for the error. And then with a confidence interval of 85%, my alpha is 15%, and you get the Z alpha over 2, Excel, Google Sheets, table, or Python at 1.44. And you get the standard error to be $219. And therefore, that gives me a difference in the population mean. Look at that. Population of the mean cost of the population of cars with additive minus the mean cost of population without additive is between minus $414 and $24. Okay? What does this tell us? So 85% of the time, the true difference is going to be between, is going to cost $414 less or $24 more. Okay, that's what this is telling us. Now, there's a caveat here. What if, so the mean, the true difference in means is between those two values. What is between those two values? Is there a zero between those two values? Yeah, there's a zero between those two values. What if our true difference in the mean is zero? It means there's no difference between the two populations. So this tells us that actually we don't have enough evidence, because zero is in between those two numbers, we don't have enough evidence to say that doing the fuel additive actually reduces repair costs. Yeah. Yep, even if it was minus 414 to 1. The fact that there is zero there in between just rules out that you have no evidence for this. Okay? So that's always the case. If your confidence interval for the means contains zero, it means you have no evidence that actually the treatment worked. Okay? So this leads us to doing some decision making. If the confidence interval does not include zero, then there's a statistically significant difference between the two treatments or the two population means. If the entire confidence interval is positive, obviously then mu1 is greater than mu2. If the entire confidence interval is negative, then mu1 is less than mu2. Now, if it includes zero, we don't have evidence to conclude that there's a significant difference. Okay? You know, so like, yeah, there's no difference. Don't use the additive because you're paying extra for the additive. Who knows what else it's messing up with your car, right? So there's no evidence for that. Now, a comment on the confidence interval. What do you choose your population to be? It's up to you, and we'll see that with the radon data. Depends how you want to phrase the sentence. So if I'm looking at the radon data or the temperature in my garage, I want the first population, or mu1, to be after the treatment so that I can say, yes, it reduced the effect of radon or the temperature, so that my confidence interval becomes negative. Okay? If I had chosen the other way, the answer would still be correct, but it's kind of easier to understand when you're optimizing for a certain effect as your result. It will be the correct answer still, however you choose your populations. But that's kind of one tip for you as you're choosing which is population 1, which is population 2. Think about what that's going to impact on your confidence interval. Like with the radon mitigation, I am expecting a reduction in radon. So that means if I choose radon after mitigation to be my population 1, so that means mu1 is going to be less than mu2. So after mitigation is going to be less than before mitigation. And then the confidence interval will be negative. It kind of strengthens that idea psychologically. Okay, just a little tip. All right, so now we did this with a known sigma, okay? But in practice, we don't know what the population standard deviations are, okay? And that's the more realistic case. So similar to what we did for a single population, where when we didn't know sigma, we had to use the sample standard deviation S, and we also had to use the t distribution instead of the standard normal distribution. Again, I'm going to write this in terms of the variance, which is the true universal formula. Then we do the same for the difference of means for two populations, and then the same way we did here for when we knew what sigma was. What I do, I replace z with the t distribution and sigma with the S distribution. So this would be consistent with the one above. So this would be the variance of x bar minus y bar, but based on the sample standard deviations. Okay? So that's it, just another formula. Now we have an issue here because the t distribution, if you remember, is completely characterized by its degrees of freedom. and that degrees of freedom was the sample size minus 1, correct? Was sample size minus 1. Here we have two samples. We have two sample sizes, N1 and N2, right? So which one do we choose? There are a few choices out there. The most conservative choice that gives you the worst case scenario is to choose the smallest degree of freedom. Why? Because when you look at the t distribution, the smaller the degree of freedom, the more spread there is in the distribution. So that captures more uncertainty. Okay, so it gives you a very conservative estimate. Okay, and typically that's something I recommend using. And it's not like I've done statistics for 50 years, but like, you know, as I've worked through the problems, like, yeah, that may make sense. It does the job. And, you know, there are slightly more advanced formulas for more sophisticated statistical calculations, but this does the job for the most part. Okay, so we'll do an example, and then we get to the radon data. Why I didn't do the radon data previously? Because I didn't know the population standard deviations, right? So we're going to use sample standard deviations. It's going to be a fun exercise. Okay, unhappy with the class she is taking. Obviously, none of you here, right? Unhappy with the class she is taking, Misty believes that the difficulty she is having in the class is the result of an inexperienced teacher. Okay, she believes that students in her particular class, I hear chatter over there saying like, this is not true, you know, don't blame the professor. She believes that students, it's always the professor's fault. She believes that the students in her particular section or class are receiving lower scores on their exams compared to students in another class with a more experienced teacher. So if there were two sections of statistics, you know, this one taught by me, the other one taught by, you know, Zach and Ariana. You know, the students in Zach and Ariana's class are doing so much better than getting higher grades, right? And, you know, you think it's because the first time I'm teaching stats, right? So that's kind of the setting. Okay, so she decides to, you know, be a good scientist, and she collects, she waits like at the outside when exam 1 or 2 is done, and she starts collecting like, you know, the grades or the exams to grade them and see kind of how the students have done, or she somehow hacks into my computer to get all the grades. Anyway, so she collects exam scores from a random sample. Don't do that, because I will hack you back. She collects exam scores from a random sample of 11 of her classmates and calculates a mean exam score of 75 with a standard deviation of 8. Misty then collects data from a random sample of 9 students in the other class and calculates the mean exam score is 82 with a standard deviation of 5. Okay, so assume now that the population distributions of exam scores are normal for both classes. Why did we have to assume that they're normal? Because the sample sizes are below 30, right? And in general, they are normal. I've seen that. I've seen a few bimodal distributions. It's unusual. Most of the time, your grades are normally distributed. Okay? So it's a fair assumption. You need to assume that because the sample sizes are less than 30. Construct a 90% confidence interval for the true difference between the mean exam scores for the two classes. And does it suggest that the inexperienced teacher's class is receiving lower scores than the experienced teacher's class? Okay. All right, so let's do this. So we're going to call population 1 the class with the inexperienced teacher. Okay, why I chose that? Because I'm thinking about the confidence interval. And if I want to show that the class with the inexperienced teacher is receiving a lower score than the class with the experienced teacher, then I want my confidence interval to look negative if it's true, if that's true, right? So then I choose population 1 to be the population with the inexperienced teacher, where I expect the mean to be less. Okay? And notice the words I'm using. I expect the mean to be less because this is going to lead us to hypothesis testing. Later we're going to say my hypothesis is that this class, not this one obviously, but the class Misty is taking has less scores. Okay? So in population 1 and 11 students, mean 75s, Sample standard deviation is 8, and population 2, sample 2, 9 students, sample mean 82, and sample standard deviation is 5. Point estimator is mean of sample 1 minus mean of sample 2, which is minus 7, so that's 75 minus 82. You get minus 7. Degrees of freedom is the minimum between N1 minus 1 and N2 minus 1, so that's 8. That gives us the t-distribution with the most uncertainty. Confidence interval is 90, so alpha is 0.1, and alpha over 2 is 0.05, and you get t alpha over 2, 1.86. You plug and chug, and you get a standard error of 5.45, okay? So now that error, we're going to take x bar minus y bar, sorry about the 1 here, x bar minus y bar plus or minus e to estimate the difference in means. So let me just fix this here. And then the difference in population means with 90% confidence is minus 12.5 points and minus 1.5 points. So indeed, Misty's assumption that her class has lower scores than the other class just from the sample is true. Okay? That is true. Now, whether this is due to the inexperienced teacher or not, that's a different question to ask, right? So obviously there's a correlation, but I don't think there's a causative effect here. So be careful in how you interpret statistics. Always ask, doesn't necessarily make sense. Okay. Now both of the endpoints are negative numbers, right? So that says that class 1 with the inexperienced teacher, they're receiving less points than, on average than the other class. Okay. All right, shall we look at the radon data? Yeah, it's a fun problem. That's as close as I'm hoping to get with larger data sets, more realistic data sets. And actually, this was the first time and the opportunity for me to actually test if my radon system is working or not. Okay, so let's do it. Open up a Jupyter Notebook, and if you go on Canvas, there's a module under modules called radon data or radon analysis, whatever I called it. And literally, I remember only 5 seconds ago. I created this morning. I don't remember what I called it. So it's somewhere there in the modules. There's 2 text files, radon before and radon after. Very simple. There's no complicated data, just a list of radon values, okay, taken over a long period of time. Do you see it? It's unpublished. Okay. Inexperienced teacher. All right, let me do this. Canvas, just publish it. Okay. Okay, so open your Jupyter Notebooks in the meantime, and you're going to load, you are going to load these text files, publish module, and all items. Okay, it should be visible now. So put those 2 text files next to your Jupyter Notebook. Okay, we're just going to do very simple loading of data. Nothing fancy. I am going to create a new notebook. New pop-up locked. Okay. Okay, so let me just name it and say in class on data analysis. All right, so we're going to do very simple data extraction. I know data extraction from CSV or Excel files is actually very important for your life and labs, etc. I might dedicate a session to working with those. We would have to be using pandas. But I'm more worried about the post-processing of the data, because the processing of the data, you can either get processed data or have GPT just parse it for you and give you cleaned up data, and then you work with the data. So I'm more worried about the analysis part than the pre-processing part of the data. It is important, don't get me wrong, but it's not urgent and important. It's just important. Okay. I mean, you remember the Roosevelt matrix, right? Urgent and important, important, urgent, not important, right? So, okay. So let's import our standard boilerplate, NumPy, Matplotlib, stats, and this SVG graphics thing. So we get beautiful looking plots. Okay. Okay, those in the back, you good? Can see? Okay. All right. So this data is processed in a way that I can just simply load it. It's a very naive data format. So just simple text. So if you open the files, actually, you'll see just radon data before and after. So it just looks like this. So these are data taken every 10 minutes, PCI per liter, okay? Just numbers, all right? Just numbers. And these are the relevant data sets for actually the same dates, but before mitigation, after the mitigation. So year 1, year 2, remember last time we said we need to pair them. We're not going to pair them for a second now, but they're consistent data sets, okay? That's what you need to care about. Radon before. So we're going to create an array. Radon before array, let's say, is equal mp.load txt. And then if you press shift tab, if you press tab, it's going to suggest radon before. Okay, so that's radon before. And then radon after array, or data, you want to call it, mp.load txt. And that's radon after. Okay, very simple. Now, if you're in doubt, we haven't used a lot of in doubt printed out this year because it's not numerical method. I'm going to miss that. I'm going to miss that a lot. We used to say in numerical methods, if you're in doubt, print it out. So just kind of print the data if you want. Radon before array. And if you print it, it's a lot, doesn't give you much. It's a lot of data. You actually need to plot it to see useful trends. Okay, so we can actually plot this as you flirt with the data. plt.plot radon before array. So radon before array, and I'm gonna do like I just keep it like this. And I'm not doing an x-axis value because I don't care about the time value where this was measured. I trust that they are matched. So on the x-axis, I don't care what unit. I have just an index, data point 1, data point 2, data point 3. And then radon after array. Let's see. And you get this plot, right? So the radon before is a lot. And then radon after. I mean, obviously, visually, you can say that this is doing something. But I'm really worried about here. I mean, even if it lowered it, what if the orange is still above the threshold of 2.4, right? So one way to clean this up is to do a semi-log y. Semi-log y. So you can just, as if you're zooming into that y-axis, right? OK, so that's a little bit better. It doesn't look as intense as before, but that's a log scale. Right? It expands that, all of the data, and you can see more of the variation. Okay? And I'm just flirting with the data now. If you receive data, what do you do with it in statistics, right? Just kind of, so yeah, I'm courting the, I don't know what's another word? Aaron, what's another word since you started this? What's another word for working with the data? Working with the data, it's boring, man. Flirting with the data, let's keep flirting with the data. Okay, so, you know, as people who flirt with each other ask each other about the mean and their standard deviation, right? So let's ask these data about their mean and their standard deviation, okay? Now, when you go on a date, don't ask the other person, what's your standard deviation? Oh, gosh. Sorry. Okay. All right, so now, again, I'm doing descriptive statistics now, okay? Just descriptive statistics. I want to get the mean value before, mean value after, standard deviation before, standard deviation after. It's not enough to make a conclusive decision. As we've learned, we need a confidence interval, but it's good to just look at the numbers. So mean before is equal mp.mean, and all we have to do is write on before array, and then standard deviation before, okay, np dot standard deviation, and then radon before array. Now my degrees of freedom here for the standard deviation is 1 because this is a sample. So remember, the sample standard deviation has n minus 1 under the square root in the denominator, and the way you get that is you put degrees of freedom is equal to 1. Okay, because it's a sample. And then mean after is mp.mean, radon after array, and then std after is mp.std, radon after array. And let's print them up. Print before mean before is equal to mean before. I'm just going to speed this up a little bit. Mean after stdev and stdev before and after, std before, std after. Okay, and I print them. Okay, so the mean value before was 2.8 pci per liter over that entire period. So that's about, I think, 2 month period. I don't know, I don't remember. Mean after is 0.57. That's a huge drop. Okay, so it's doing something, but I'm still not confident that it is true for the population. What is the population of radon? It's all years, all the time, every day. Okay. The standard deviation was 3.7 before, so there's a lot of spread. The data is all over the place before. Notice it goes up to 60 and then goes down to 1 and then goes up to 20 and then goes down to 1. After, it's like varies between 0.1 up to 1.5 or 2 and then kind of stays around that. Okay. Standard deviation after is 0.27. Okay. So we're starting to have evidence that the system is working, money well spent. Okay. Let's do a histogram now. And you're doing histograms for your homework only on the data before, right? So let's do a histogram. I'm going to do a histogram before and after. plt.hist of radon before array. And I'm going to do bins, let's say 50 bins. And then plt.histogram radon. Obviously, I can make these plots much more beautiful, but I'll do that for a publication, not here, right? And okay, so sometimes you get this stuff, you just put a semicolon at the end, and you get this. It's not very pretty. There's a lot of just nothingness over here. Okay, there's a lot of nothingness over here. So let's do a slightly better job. One trick you could do is to define your bin edges. Okay, so let's define our. So remember the bin edges when we did in the beginning these descriptive statistics. So you can define those with Python. In Google Sheets we were not able really to define them. We might have been able to define the bin centers. So in Python you can define bin edges. It takes a little bit of work, but here's a trick I learned. So you can just do this as a linspace, and because all of this. So first, do we understand what this means? Okay, can someone explain this to me? Like, let's just look at the blue is the data before. What does this mean? So the x-axis is what? Radon concentration. So, here at this point, you have between 9 and 10 PCI per liter, you have what? Maybe 90 values, right? For this guy over here, between, let's say, 4 and 5 PCI per liter, you have 100 entries, 100 data points, right? So over here, where you have, what, 1,500 data points, is kind of between 0.1 and 0.5 maybe, right? So, histogram with values, not a density histogram. You could do a density histogram, gives you a percentage. But let's first kind of clean this up a little bit. So the bin edges, now anything above 10 is probably going to kill you, right? So really what I want to see is here. I'm just going to drop these guys. There's not much going on here above 10. Okay, but anything, the threshold is at 2.4 for the EPA. So I want to look in this region. So let's define our bin edges up to 10 and put 50 bins, and you can use this for your homework. So we're going to go from 0 to 10 and put 50. And then all you do here is say bin edges. And then bin edges. Let's see what it does. All right. OK, this is better. And we can do a density now if you want. Density equal true. And density equal true. OK. OK, great. Now the orange is after, the blue is before. Is the orange better? Let me remove the density. Let me remove the density. So the orange is after, okay, but the blue is before. So maybe I put a transparency so we can see what's going on. Okay. It's the count. How many data points do I have over all of those data? Okay. So think of it, how many minutes did I measure this concentration? How many times? Just the count. So is the orange better? Why? Yes. Yes. I don't care how big this peak is. It could go to infinity. Actually, that's better because it's telling me most of my data now is below 2. What it did, it took this histogram and shrunk it all to between 0 and almost 2. This is great. This is great evidence. The value on the y-axis, if it's larger, doesn't tell you, oh, it's worse because it's larger. What you're looking at the graph here is the spread. In pre-mitigation, I have concentrations above 2, which is concerning. 200 times out of these measurements, I have, 3 concentrations, 3 PCI, 4, 6. What if I'm spending all my time in the evening at those concentrations in the basement? I'm playing guitar and, stuff. So, right? That's bad. But here, I moved all the data. And where is the data going to go? It's going to all build up. So this has to go higher because it's a lot of data, right? It's just pulling them all into these bins, right? So this is even stronger evidence that it did something, okay? Money well spent. All right. Let's now do an unpaired analysis. So truly, in this case, analysis, the data should be paired because it is the same house, it's the same sensor, it's the same time. We talked about this at the beginning of this unit, the data should be paired. The pairing situation is a little easier, actually, than the unpaired situation, but I'm going to treat those as unpaired, and I will still get similar results. All right. So I have the mean before, standard deviation before. Let's see, what do we need to do? We need to compare the two means. Let me get you that formula. Okay, if I move this here. So what I'm after is computing this standard error E, which is T alpha over 2, the critical T value. Square root, I have S1, I have S2. We just computed those. I have N1 and I have N2. I just need to compute T alpha over 2. And that's it. And I can get my confidence interval. Okay? So let's do that. Okay. So N before is going to be the length of radon before array, and N after is going to be the length of the radon after array. Okay, and then the point estimator, point estimate. So that's going to be population 1 minus population 2. We decided to do to call population 1 as after mitigation. Why? Because then if the confidence interval is negative, it's going to tell me that yes, I've reduced the mean value. Okay? The mean value after is less than the mean value before, so you get a negative confidence interval. Psychologically, it has a stronger effect when you tell the story that way. Okay? We're not manipulating the data. We're clarifying the data. It's easier to comprehend for people. Okay? All right, so let's do the point estimate is going to be the mean before minus the mean after. Okay, that's my point estimate. And then my standard error. So I will need the T critical, actually. So confidence interval. C is 0. What confidence? Let's say 95%. Okay, so alpha is equal to 1 minus C, agreed. And then the critical value, T critical, I can get that from the T distribution. So that's going to be stats.T, right? So that gives me the student's T distribution, right? And what I'm after is this PPF. That's the inverse. That's the essentially give you the T score, right? So we're going to give it a probability here, which is alpha over 2. Degrees of freedom. I'm not going to touch those things. They don't matter in this case. Okay? So what we will do is stats.t.ppf. Okay? And I'm going to do 1 minus alpha over 2. And then my df is equal to my degrees of freedom. So what is my degrees of freedom in this case? DOF is equal to np.minimum. N before minus 1 and N after minus 1. Agreed? If you look at the slides here, my degrees of freedom is the minimum of N1 minus 1 and 2 minus 1. Okay? So my DF is DOF over here. Okay? Now the T distribution is symmetric, so whether you put alpha over 2 or 1 minus alpha over 2, you'll get just the same value, but with possibly different signs, so you got to figure that out. Okay, so that's my T critical. And then finally, I can do my confidence interval, CI, confidence interval on means, is equal to, I'm going to put that in a tuple. So we will do point estimate minus, oh, I didn't compute E. So let's compute E. E is equal to T critical, right? So that's T alpha over 2 times MP dot square root of S1 squared over N1 plus S2 squared over N2, right? S1 squared over N1. Okay. So times STD before squared over N before plus STD after squared over N after. Okay? And then point estimate minus E, and then point estimate plus E, and then print. Let's see. With 95% confidence interval for after and before mitigation. And that's equal to CI confidence interval on the means. Okay? And I get an error. Very nice. Very nice. NP dot, oh, not NP dot min, just use min. All right. Okay, so my point estimate, oh, I should have done mean after. So we get a negative value. Mean after minus mean before. Okay. Okay. So then, 1 second, Soren. So then my estimate of the true difference that I've dropped with 95% confidence in the mean value on my radon concentration is a negative. So it means we drop the value minus 2.35 to minus 2.11 PCI per liter. So the system works. Okay? The system works. Now that's the drop in the mean value. Okay? But you still have to look at the mean value itself, because if the mean value is 50 and I dropped it by 2, it doesn't matter. It's still gonna kill me, right? So that's why we did the descriptive statistic in the beginning, just to get an idea of where that mean value is. What was your question?
What's CI mean again?
Confidence interval. Okay? So yes, we dropped by 2.35 PCI per liter, or 2.11. But still make sure that your actual mean value is below the threshold of 2.4. If my mean value after mitigation is still 10, so you can do a confidence interval on the sample after, right? So you can do a confidence interval on that one, easy, right? Same thing, T alpha over 2 square root of S squared over N, right? And that mean is going to be about 0.5. Okay? So this says that the system works, and also I'm sure that my mean radon levels after is acceptable. Okay? Now, if the before value, if the values before were, if the mean value before was 10 or 15, right, I would actually expect to see a larger drop, because these systems, they work when they do work. Okay? So I would have seen a drop of about 15 PCI per liter. Okay? But anyway, so keep things in context, and I'm happy actually. This is the first time I wanted to do this since we installed the system just about almost a year ago, and so this is great. And I have skin in the game. It makes a great for a great example. It's engineering. Okay? Always doing like crazy stuff around the house. So we're going to be doing the garage data. You're going to be helping me assess the garage temperature, if it works or not, okay, in the homework assignment, okay? Okay, literally like my temperature, so I have a 3-car garage with the doors are west facing, and an entire wall, so what, 24 feet deep, and about 15 feet high with the attic and whatever. It's all south-facing, baked in the sun. It's uninsulated, because it would have cost them $50 more to do it before they put the drywall. So I measure temperatures of 125 in the garage, Fahrenheit. My bikes, the rubber on them was melting. The tools were just deteriorating. So it was like a cost-benefit thing. We need to install. So we would bake in there. We just go do Bikram yoga in there. It's insane in the summer. So anyway, we'll analyze that in the homework assignment. It's a fun exercise, similar to what we did here. Okay. All right. So okay, perfect. We're done with this. There's a special case. So far we compared 2 populations with independent, so unpaired, with known sigma. So that was the first example where a simple example where we knew sigma. Next, we did unknown sigma. We approximated sigmas using the sample standard deviations, which required us to use the t-distribution. There's a special case when they're independent samples. It's an unknown sigma, but your best guess is that the populations have equal standard deviations, okay? Say, heights among men, and you're doing this or that. Well, the heights among men, two populations, even like men at school or men not at school, right? They have the same standard deviation in heights. I guess taller guys end up at the back. I don't know. Anyway, but like that's the sort of thing, okay? So this is a special case when sigma 1 equals sigma 2. It just simplifies the formula. Well, it provides a more accurate formula for the confidence interval. But you don't have to use it because you can always treat them and assume that they are different standard deviations, okay? So this is a special case. It doesn't rule out the case we did before. This is a special case of the case we did before, just provides a more accurate formula. And this is called data pooling. So when it's just, I don't know why they even use that word. I don't think it's called data pooling, but they call it data pooling. And in this case, the formula changes a little bit, okay? And we still have the estimator. So when sigma is the same, you can simplify the variance a little bit because you don't have sigma 1 and sigma 2. You just have sigma squared, right? So, it's still the same formula, except rather than having sigma 1 squared here, sigma 2 squared, it's sigma squared. You pull it out of the square root, you get a sigma. Okay, so this is still the standard z-score for the random variable x bar minus y bar, okay? That's still the same. Now, with this simplification, we say we're going to pull the data, and the estimator for the standard deviation. So two populations, they have the same standard deviation, but we have two samples. Which sample do we pick to estimate the population standard deviation? We say we pull the two samples together, and Lord knows, coming up with a formula for pooled data. So when I tell you we're pooling the two samples, this is the formula you will use for the standard deviation estimate. So this becomes a point estimator for the population standard deviation. We have two populations, but they have the same standard deviation. Two samples, they don't have the same sample deviation, but we can pool them together to estimate the population standard deviation. And then your estimate is still the same, except now you're using this SP squared. So it becomes a nasty formula. Okay, it's just more algebra. Okay, more algebra for the standard error estimate. You still have a t-distribution because we are using a sample standard deviation in place of a population standard deviation. Okay. The trick here also with the t-distribution is that the degrees of freedom is no longer the minimum of n minimum of the degrees of freedom of each sample. Because we've pooled the data together, we're going to add them up, actually. Degrees of freedom of sample 1 plus degrees of freedom of sample 2. So it gives you n1 plus n2 minus 2. Okay? Just in the end, you're going to have a long table of if this is the case, do this. If that's the case, do that. If that's the case, do that. We do our best to try to explain where these are coming from. And eventually, you're going to forget, but at least hold on to some basic concepts. Like, okay, when I don't know the standard deviation, I use a t-distribution. Okay, when I'm comparing two populations, I'm looking at the random variable of x bar minus y bar, not x bar alone and y bar alone and taking the difference. And in the end, you just kind of look it up from textbooks, okay? So, yeah, this is the formula, the usual way we do these things. And let's do an example. Obstetricians are concerned that a certain pain reliever may be causing lower birth weights. Actually, we went through this, and it didn't affect us. But certain pain medicines. I mean, it's hard. Pregnancy is like insanely complicated. Like I don't know how. Like it's a miracle, man. It's like I don't know how humans give birth. Like a hugely complicated process. And it's painful eventually, baby, becomes heavier and, you got back pain. and mom is in pain, you know, you want to do everything to provide comfort. So pain medicines are always an option. However, their life in the body, we don't understand their impact on, they say, birth weight, heart rate. You take a adult-sized dose Tylenol, say 3,000 milligrams a day. How much of that is getting into the baby, right? And it could cause liver damage, as you understand. Tylenol, for example, ibuprofen messes up with the stomach lining, causes bleeding, etc. How much of that is getting into the baby, right? And so all of these things you got to worry about. Anyway, so a medical researcher collects data from a random sample of 12 mothers who took the pain reliever while pregnant and calculates that the mean birth weight of their babies was 5.6 pounds with a standard deviation of 1.8 pounds. So that's the sample standard deviation, okay? And she also collected data from a random sample of 20 mothers who did not take the pain reliever while pregnant, okay? And calculates that the mean birth weight of their babies was 6.3 pounds. So, okay, it's a little high, they're a little bigger, and a standard deviation of 2.1 pounds, okay? So, well, it looks like, yep, the pain medicine is lowering birth weight if you look at this, just the numbers like that. But we're becoming statisticians. We know that you cannot make a claim just based on sample means, okay? Assume that the distribution of birth weights is approximately normal. It is, and why? Because we have a small sample size, 20 and 12, right? Construct a 99% confidence interval for the true difference between the mean birth weights, okay? And doesn't suggest that there's a difference in birth weights, okay? So here, you could use the formula we used before, S1 and S2, and you'll be fine. But here we want to exercise that the idea that the population variances or standard deviations are the same. And they are, because it's just, pregnant women, right? So there's no variance between them. They're just either taking the medicine or not, right? And so you could assume that the population of pregnant moms, that they have the same variance. Okay, and then you do the thing, and you do x bar 1, or should be x bar minus y bar. I don't know, I changed the notation here. But anyway, what this gives you is a confidence interval of minus 2.7 to 1.3. Okay, so population 1, what did we say? Population 1 is birth weight of babies with pain reliever versus birth weight of babies without pain reliever. So mu of babies with pain reliever, mean weight, minus mean weight of babies without pain reliever. Confidence interval, what does it contain? 0. We don't have evidence immediately. There's no evidence that it affects birth weight. It could affect other stuff, right, but doesn't affect birth weights, okay? So, yep, we cannot make that conclusion. Okay. Population proportions. I know I said we're not going to talk a lot about proportions. We're still not going to talk a lot about proportions, but I have to just keep them in your slides. If you deal with a proportion, you need to know the formula. So remember, a proportion is simply the number of items or successes or the thing you're tracking over the total size, either of the population or of the sample. Okay, so 40% of university students choose to eat in the cafeteria, right? That's the population true proportion. You take a sample, it might give you a 45% of students in the sample choose to eat at the cafeteria, right? So we call the population proportion P. Don't confuse that with probability P. And the sample proportion as P hat. The only difference is that with the sample proportion, you're counting the number. You take the sample, ask who eats in the cafeteria. That's going to give you your X value over the size of the sample. Okay, so we want to estimate the population proportion. So you're asked from a sample, you find that 45% of students eat at the cafeteria. What is the true population proportion? How many students at the university eat at the cafeteria? So this immediately tells us this is a binomial distribution, and then from the binomial distribution, we're going to jump to a normal distribution. Okay, so if you remember all of these things with the binomial, usually you don't have to worry about this anymore. You just go and and do the test. They do that all the time, whether it's valid or not. They just do that all the time. So the normal distribution can be used to approximate the binomial distribution. Remember, we saw all of this when np is greater than 10 and n into 1 minus p is also greater than 10. Then you can approximate the binomial with a normal distribution whose mean value is p. So the mean value, that's the true population proportion. And the standard deviation is square root of p1 minus p over n. And then from there, you just treat this as if it's just a standard error analysis. So when you compare the two population proportions, we're trying to estimate, we have two populations. Population, let's say, of people who ate at the cafeteria before they opened McDonald's over there or whatever, and then those who ate after they opened, right? So, okay, we want to attract more people to the cafeteria. Okay, so we're trying to estimate P1 minus P2, the true population difference, but we don't know that. We only know P hat 1 minus P hat 2. So that's going to be our estimator, right? And so we follow the same procedure we did before. So for the standard error, we had z alpha over 2 square root of the variance x bar minus y bar. Now we're going to have the square root of the variance of P bar 1 minus bar 2. And now that variance, when the samples are independent, as we stated before, then a similar formula is going to apply, which you're proving in your homework 8 for the for two sample means. And then that becomes the sum of the variances, and you get this. So you plug and chug. In the end, you're going to get a simple formula that you'll apply, and it will be this guy. Okay? You're going to get this guy. And those actually should be p hats. My apologies. So they should be p hats. There's a typo here. Let me fix it. There's a typo here. Let me fix it. Okay, so this is our standard error for proportions. You have sample 1, sample 2, sample proportion 1, sample proportion 2. You just plug in the numbers and get your answer, okay? And this is kind of how you apply. So let's do an example. In order to determine if a new instructional technology improves student scores, a professor wants to know if a larger percentage of students using said technology passed the class than the percentage of students who did not use the technology. Records show that 45 out of 50 randomly selected students who were in classes that used the instructional technology passed the class, and 38 out of 451 who were in classes that did not use the technology, they passed the class. Construct a 95% confidence interval for the true difference between the proportions of students that used the technology who passed and those who did not. Okay, so we only have a sample of students. 45 out of 50 who used the technology, they passed, and 38 out of 51 who didn't use the technology passed. Those are our samples, sample proportions. We want to make an inference about the population of students who use the technology or don't use the technology. Is it going to improve their scores? Okay, so sorry, we got to fix this projector here. So look at this projector. We know we had one. It's 45 out of 50 students, so that's 90% of the students passed who used the technology. And P2 is the population who didn't use the technology. 38 out of 51 passed, so that's about 75% of the students passed. The difference in proportion, choose population technology, population 2 didn't use the technology. So the difference in proportion is 15.5%. Okay, the level of confidence is 95%. So alpha over 2, we 1.96. You plug in the numbers and you get a standard error of 14.5%. And then your confidence interval is going to be 0.9% to 30%. In other words, they've improved those students who use the technology have improved their scores, okay, by about 1% to 30% score improvement. Okay? So this suggests that yes, there is, although the lower end of the interval is 1%, that's not much. But you could be, you don't know where you could be at. You could be closer to the 30%. What this says is that, yes, instructional technology does make a difference, makes a little difference, okay? Is it worth the effort? I don't know. If it's costing you 50 hours a week to just do that extra technology, maybe it's not worth it, right? Okay, but for you guys, anything, it's totally worth it, so. Okay, all right. Comparing two population variances. So actually, I have 2 minutes, so I'll let you go. We'll finish. This will spill over on Thursday. We'll do some of it and start on hypothesis testing, okay? Thank you so much. Godspeed. I want to finish with these population treatments so you can do it for the homework, and this will be included in your exam. So if you remember, this unit we were talking about comparing two treatments or two populations, two samples, and we covered the situation where we're comparing means with a known standard deviation, means with an unknown standard deviation, and then proportions, okay? And all of those data were unpaired. In other words, the samples were independent, unrelated to each other, just randomly selected. We still have two things to do with these comparisons. The first one has to do with variances. So we compared means. Next we need to compare variances. Variances are important, and I was hoping to cover that in the class at the end, because variances relate directly to uncertainty. In other words, when you're taking, for example, repeated measurements, and the measurements follow a distribution, that variance in the distribution is directly related to the uncertainty in your knowledge of the truth, okay? So variances are important, and when you're doing analysis, let's say you're taking a measurement, and then you're processing the measurement, and then you're taking another measurement, and doing something to it, and making a calculation, that uncertainty propagates in very strange ways. Sometimes it cancels out, sometimes it compounds, and doing this sort of uncertainty propagation is an important piece of engineering, especially in laboratory analysis as well. So if we have time at the end of the semester, that's a topic I would like to talk about and discuss with you, excuse me. So the point is, it's important to look at variances. And the case we're going to look at is the variances between two populations with independent samples. There's no question whether you know sigma or not, because you don't. You're looking at two samples. We're going to take their standard deviations from the samples and try to compare them. Now, it turns out that with the means, when we took the difference between two means to compare the difference between two populations, when it comes to variances or standard deviations, it's not the difference that matters, it's actually the ratio that matters. Just because of what the variance means, because the variance is always something relative to a mean value. The mean value, in a way, is an absolute number, and when you compare two mean values, it means something. Okay, the average height of this sample, or the average repair cost for this engine versus that other engine, you take the difference, that means something. That's a nominal value, sends out in its own self. But it doesn't make sense to take the differences between variances because it really doesn't tell you anything, because the variance is only relative to a mean value. So what makes sense is taking the ratio of the variances and comparing the ratio of the variances. You can take the differences, it's just not going to tell you a lot of information. The ratio is going to tell you more information. So for example, if the ratio is 1, you know that there's no difference in variance between the populations. So if our confidence interval is going to contain 1, then we know that this is likely statistically insignificant. Now, again, we have two populations, population 1 and 2. S1 is the standard deviation of sample 1, S2 standard deviation of sample 2. However, this ratio is always built by assigning population 1 to the population or the sample that has a larger standard deviation. So you have two samples, you look at their standard deviations, make population 1 the one with the larger standard deviation, and population 2 the one with the lower sample standard deviation, so that you can build that ratio. That's by convention. Now, this is a point estimator for the ratio of variances between two populations. Just like the difference between two sample means was an estimator for the difference between two population means, it was a point estimator. Just like S was a point estimator for a single population, the ratio of two sample standard deviations is a point estimator for the ratio of two population standard deviations. Now, S1 squared over S2 squared is distributed according to the central limit theorem. So if we were to run the experiments we did before and run the statistical simulations, which we will not do now, we just don't have time anymore, this ratio is distributed according yet to another distribution called the F distribution. This is probably like the last distribution we're going to have to learn as we do statistical inference, okay? It's called the F distribution. And like the T distribution, which required 1 degree of freedom, the F distribution requires 2 degrees of freedoms. Guess where they come from? From population 1 and population 2. Okay, and typically when you see this in Python or in Google Sheets or Excel, you'll see DFN and DFD. DFN stands for degrees of freedom in the numerator, DFD, degrees of freedom of the population in the denominator. Or D1 for the numerator population, D2 for the denominator population, or population 1 and population 2. It looks like this, just plotting that F distribution. Obviously it changes a lot depending on those 2 degrees of freedom. But that's how S1 squared over S2 squared is distributed. Now from that distribution, we're gonna then build our confidence intervals, because that distribution gives us a probability density for finding a certain ratio within a certain range, okay? That's why this is so useful. I have some points here, bullet points for the F distribution. It is always skewed to the right. The values of F are always greater than or equal to 0. The shape is completely determined by the 2 parameters, DFN and DFD, or DF numerator, DF denominator. Now, in a similar fashion, it's a little bit more complicated to derive this, so I'll not derive it, just throw the formula at you, and hopefully you trust me enough now that I'm giving you correct information. The confidence interval is no longer a plus or minus based on an existing value like we did with the mean value. With the mean value, we had the population was between X bar minus standard error and X bar plus standard error. This is not the case here. And in fact, your great TA, Zach, came to my office this morning and said, you made a mistake, Professor Saad, in the answer key, and I took the difference between standard deviation. So it was wrong. This is the confidence interval for the ratio of standard deviations. Now remember what we're trying to do here. We have samples from 2 populations. We're trying to estimate the population standard deviations. We have samples, they have their own sample standard deviations, S1 and S2. What can we say about the population standard deviations? This is what we can say, that the true ratio of the population standard deviations, population 1 over population 2, is between these 2 values. All right, and you will see we have, similar to the chi-squared distribution, where we had alpha over 2 and 1 minus alpha over 2, it's not symmetric, so they're not equal and opposite in sign, because the F distribution is always positive and it's not symmetric. F alpha over 2 is going to be the larger value on the right side of the distribution, and F1 minus alpha over 2 is going to be on the lower side of the distribution. Okay? Another way to think about it, F alpha over 2 is the inverse z-score on the F distribution, so that's the inverse, F score on the F distribution, such that the area to the right is alpha over 2, same to the chi-squared distribution, and F1 minus alpha over 2 is the F value such that to the right, the area is 1 minus alpha over 2, okay? So F1 minus alpha over 2 is the smaller value, F alpha over 2 is the larger value. Okay, keep that in mind, because different functions in Google Sheets and Excel and Python, they say, oh, I'm gonna give you the left, give me the left area or the right area. Just whichever one you use, make sure you understand what the function you're using wants as input, okay? Now, in terms of degrees of freedom, similarly, always the degrees of freedom is sample size minus 1. The numerator degrees of freedom is N1 minus 1. N1 is for sample 1. And for the denominator, or DF2 or DFD, we have N2 minus 1. Okay? So you plug those numbers, you get the F alphas, and you're done. And same thing, so this is the variance, and the standard deviation is simply the square root of that. So you take the square root of this and operator, and it preserves the inequality. So you can either apply it on the variances or apply it on the standard deviation. Make sure your units or dimensions for these quantities are correct. Variance is always dimension squared, unit squared, and the standard deviation is in the same units as the independent variables. Okay? So essentially the way we proceed with this, we find the point estimator, and then we compute the f alpha over 2 and f1 minus alpha over 2 based on the confidence interval, substitute, and move on with life. So it's just a matter of calculation from here onwards. And mostly that's how it's going to be for the remaining lectures. Here's an example. A family nurse practitioner, FNP, I don't know why they put that. Like, I don't need to know the acronym of a family nurse practitioner. Just call her the family nurse practitioner. Is comparing the variability of normal body temperatures for infants and adults. Okay, she wants to know if the population standard deviation of normal body temperatures is the same for infants as for adults. That's an interesting question. Actually, the heart rate. So when we were pregnant with our first boy, Mark, we went on like the 3 months test, and the doctor was taking the heart rate. It was like 127 beats per minute. I'm like, why is it so high? So I was like, yeah, all babies, have high heart rate. I was like, why? She said, I don't know. And we started thinking and like talking about it in the room. I was like, it's probably because the blood vessels are so thin and the heart is so small and trying to keep up with all that pressure, so it beats faster to try to pump that blood, right? But the system has a lower pressure difference, and so anyway, she thought it was interesting. I told her, if you write a paper about it, tell me. But anyway, I'm sure there's a very good explanation for that. But yeah, it's very interesting. Okay, so a simple random sample of 28 of her infant patients' normal body temperatures measured in degrees Fahrenheit reveals that they have a sample standard deviation of 0.567 Fahrenheit, and a simple random sample of 25 of her adult patients, normal body temperatures, also measured in degrees, have a sample standard deviation of 0.663. It's rare to find a doctor who treats infants and adults. Like right now, it's kind of very hard. My doctor back home where I grew up just treated everything. Also animals, everything. It was a doctor. He was like the town doctor. I'll fix all your ailments, even repair refrigerators and stuff. Anyway. I think he was also a priest or something. Okay. So assuming that both populations, assuming that both populations are normally distributed, we need this because our sample size is small. Okay? So you have to make that assumption. All right? And that's reasonable in most medical things, and things are normally distributed. So that's fine. Assuming that both populations are normally distributed, construct a 95% confidence interval for the ratio of the population standard deviation. So we only have sample standard deviations, and I don't know, they're close, maybe not. I don't know how big of a deal. Half a degree difference might mean, you're slightly feverish or not, because body temperature is normally stable, right? So I think it's an important variance, these two. Okay, so we have the sample standard deviations and variances. We want to infer something about the population. Is it that different in the population, in the true population of adults and infants? Okay. So first we make sure that the conditions are met, and they are met. Okay. And this is a summary of the data. So I like to put it this way so I can tell which one is going to be population 1 and which will be population 2. So on the first column, I have sample size, sample standard deviation, and degrees of freedom. And on the first row, I have adults and infants. So we have 25 adults, 28 infants, 0.63 adults. That tells me adults is going to be population 1 because it has the larger standard deviation. And 0.567 degrees Fahrenheit is for the infants, so it's going to be S2. Degrees of freedom is going to be n-1, so 24 for adults, 27 for infants. First, we get the point estimate, S1 over S2. That's 1.17. And then with a confidence level of 0.95 or 95%, alpha is 5%, therefore alpha over 2.0, so 2.5%. And then I need the 1 minus alpha over 2, which is 0.975. Then you go and plug this in Excel or Google Sheets. It's f.inv, or in Python, it's stats.f.ppf, either one of those. And then you pick up the tables in the statistics textbook, and you get these numbers. And and if you're confused about here, like, okay, which one you picked here, the smaller number is always going to go on the right of the interval, right? Because it's in the denominator. Okay, so you want a smaller number in the denominator to give you a larger value on the upper bound, and the larger number is going to go on the left side of the interval because you're dividing by a larger number. It's going to shrink that value, and then you get a ratio between 0.78 and 1.7 degrees. Okay, what does this say about the populations? Are they different in terms of variance? So what we're asking here, what we're saying is, from the information we have from the samples, we are inferring with 95% confidence that the population ratio of standard deviations between adults over infants is anywhere from 0.8 to 1.75 degrees. So sigma adult over sigma infants is between 0.8 and 1.75 degrees. Does that mean that the two populations have the same spread, or one is spread more than the other? So the true population ratio is going to be anywhere between these two numbers. What's an issue here between these two numbers? Yeah? One is in between them. And however small the chance is that the true population ratio is going to be 1, it is in there. There's a likelihood that's going to be in there. So therefore, we cannot rule out that these populations are different. They're actually, we don't have enough evidence to say that they're different. And in fact, we can say that the uncertainty or the variation in the data in body temperatures between adults and kids is about the same. Okay? Well, we're the same, right? You grow up, you still kind of, body varies. Although I feel like as I get older, I get colder more often, right? And I have to put on more layers. So, but it doesn't mean my body temperature is different. It just means I'm more sensitive to temperatures. Okay? Okay, one last shot and we'll be done with this. What do we do about dependent samples or paired data? So that's on your homework assignment, right? You're going to take the radon data. And we made a very strong case that the radon data, you have to compare them as a paired data, okay, as paired data. I have an air pollution sensor in this room and an air pollution sensor outside, and I'm comparing indoor and outdoor air quality. I have to match them at the same, I treat them as paired because they're connected in the same building on the same day. However, if I had pollution data from different schools and different days and pollution data from different outdoor locations at different times, those would be unpaired. But I have to have a lot of those sensors spread everywhere. Okay, so just make sure you make a good decision on whether you pair the data or not. Okay, so what do we do when the data is paired? Previously, what we did, we looked at the mean of each sample, we took the differences and we kind of compared them separately. But when the data is paired, most likely means that for every data point I'm collecting for treatment population 1, I have a corresponding data point, from sample 1, I have a corresponding data point from sample 2. What that most likely means as well is that I have the same number of data points in sample 1 as I have in sample 2. Okay, you measured for a month, inside and outside, unless the thing broke, right? But then you just take out those data points. So one can make the case, in that situation, instead of looking at the differences in averages, we're going to look at the average of the differences. In other words, I'm going to take the two samples and subtract them from each other, point by point, and create a new population or sample of differences. Okay? You're going to take the radon data before and after, or in the homework actually the garage data, the temperature data before and after the AC at the same times, take their differences and create a population of differences or a sample of differences. And you know what happens then? It simplifies the entire analysis. It's actually easier to do this. Because now I create a new random variable, call it D, okay, for difference, which is the difference between population 1 and population 2. The I means this is the data point. So D0 is the difference between the first two data points. D2, D1, second two data points, and so on. So think of it as you have an array of sample 1 an array of sample 2, you take their differences. In NumPy, you just do array 1 minus array 2, you get your differences, okay? We now have a new sample, D, that corresponds to the population of paired differences, all right? And then that, you just treat that as a single sample from a new population of differences. And then what will apply for the confidence interval is what we did for a single population. Isn't that cool? So we already know how to do this when we did confidence intervals on a single population. Except now, we just got to do one step to take the differences and create a new sample, calculate the mean of that sample, which is simply the sum of all the sample differences divided by the number of points, and then you create the standard deviation for that, and you just build your confidence interval the way we did. And then you make an inference on the mean of the difference, okay, on the mean of the difference between the two populations. This case is actually easier than all the cases we covered so far, okay? Now, in your homework, you're going to do this for the garage. And you're also going to do it for the standard deviation. You have to figure out how to do it for the standard deviation. It's not that hard. Let me show you how I do this for the radon data. Get your notebooks up, the radon notebooks that we were working on last time. All right. So let's do here, we're going to, okay, let's remember what we were doing here. We had all of these arrays, okay, histograms, unpaired analysis. All right, so now we're going to do paired analysis. Paired analysis, okay? Let's see. Okay, so I had, what did I call them? Radon before and radon after. Okay, so let's declare the D array as the difference, which is radon before minus radon after. You can choose whichever one you want, radon after or radon before. Array, the first one, doesn't matter. And then I'm going to plot the, do a histogram of the difference, okay? So if you're not convinced, what this does is you're going to take the difference point by point. So this array has 1,440 points. This one as well is going to take the difference point by point and return a new array containing the differences. If the arrays are not of the same size, it will throw an error, obviously. Okay? So what you need to do in that case, clean up the data points that don't match. If you're doing paired analysis, it needs to be consistent. It's paired. For every point in population in sample 1, there should be a corresponding point in sample 2 at the same diet, same conditions. Okay? So if the arrays don't match, don't just simply eliminate points at the end or points at the beginning. Go back to the original data and pick the data points that don't exist in the treatment, for example. Let's say your sensor broke down, for 5 hours on that day. Well, knock out those data points from the other sensor, okay? All right, so, and then we can do a histogram of the differences. Bins, let's say, equal, 50, whatever. And, okay, so now this is the difference in the radon data. It moved everything, so I'm taking at every point and moved everything to like below 10, and there's not much going on up here anymore, okay? Now, I don't know if this histogram is very useful, but I can tell that that mean of the differences is shifted, and I hope it's going to be below 2. So I can zoom in a little bit here and see where this is. But let's just run the numbers. Let's just run the numbers. OK. So let's see. So because I need now, so where's the formula? Sorry, get the formula. Thinking about something else. All right, so what I need here is the standard deviation of the sample of the sample containing the differences, so SD, and that's going to be this guy, and I can get it with NumPy directly, and then I'm going to need a t distribution at alpha over 2. Okay, great. So, because this is means, so it's a t distribution, not a chi-squared, right? It's not standard deviations. Okay. So let's do n is simply the length of D. You can print n, and that's equal, oh, well, I guess not 1440 points, something different. All right, standard deviation of the sample, it's MP dot standard deviation of D, and this is a sample, so DDOF, or degrees of freedom, is 1. Okay, because this is a sample. My confidence interval, let's say 0.9, and then my alpha is 1 minus confidence interval, right? And now my degrees of freedom is simply n minus 1, because it's just one population, right? Population of differences. All right. So now my T critical value, the critical T value, the alpha over 2, is stats.T distribution.ppf. Okay, now the ppf is going to require a probability. So I'm going to give it the 1 minus alpha over 2. Okay, so it's going to give me the smaller value. Okay, and then df. Okay, so let me call this DOF equal DOF. Okay, that's what it requires. And finally, my standard error is T critical times square root of SD over MP dot square root. Oh, no. Made a mistake. It's SD over MP dot square root of N, right? Yep, T alpha over 2 times S over square root of N. Okay? So we're looking at the mean of differences. Okay? And then I need the mean value of the sample. I'm going to do d bar, that's MP dot mean of D. Okay? And then finally, I'm going to create my CI is equal to d bar minus E, and then d bar plus E. Right, and then print CI, and it's going to throw an error. Module numpy, does not have, where's NP? Pardon me? Yeah. It's not an numpy, because I had a square root, right. Okay, so that tells me that the mean of the differences is between, so we're taking population 1 minus population 2, and that means it dropped it by 2.1, anywhere between 2.14 and 2.33 PCI per liter. Okay, so this is actually a little consistent with what we saw previously when we did the unpaired analysis, but here we took population 1 minus population 2, so, right, so the means, so 2.119 and 2.352, and here we have 2.13 and 2.33, so we're still pretty close, the unpaired analysis versus the paired analysis. Okay, it just happened in this case, but in other cases, it might make a huge difference if you do an unpaired analysis on something that needs to be paired. Okay, so make sure you make the right choice. Okay? You'll do, yes?
I might have missed this part, but is there a reason why it's positive, the other one's negative?
No, because, yeah, so that's what I was saying. Here I took population 1 to be the before, right? So the before is larger, so I can switch them. Okay, so we can do minus and plus, right? And then it's going to be, okay, then you see the negative. Okay? You see the negative. Okay? We're done with confidence intervals on 2 treatments. Okay, I'll give you a little break before we start on hypothesis testing. Okay?